Okay, so let's get started. This is lecture number 13, ECE 231, and I'm working off of the second half of the set of slides that I published on Moodle already, that one set covering lectures 12 and 13. So before we get into it, just to remind you that homework or lab assignment number 3 is assigned and is underway, so be working on that. And do stop by the lab and pick up 2 things that you'll need for this lab and the subsequent labs. And that's you'll need a small red bag of parts. Whoops. This little, pick up one of these red bags. One more time here. Okay. Pick up a red bag of parts and then pick up a set of alligator clip leads. The parts just have a motor and a temperature sensor and some other things that you're going to need. It can be tricky to connect wires to the motors, and so the alligator clip leads make that easier for you. So that's what that's about. And you'll have, and just go to the lab during any of the TA office hours and you can get those, and you can find those office hours at the top of the Moodle website. So I'm going to finish the discussion of LEDs today, and I'm going to particularly talk about this 7-segment 4-digit LED that you have. And so let me just first say one thing that can be confusing about this. A 7-segment LED is a classic display. You know, it's got 1, 2, 3, 4, 5, 6, 7 segments, right? So we call it a 7-segment display. It's also got a decimal point. So that actually means 8 segments. And so you need 8 wires. Or, you know, there are 8 anodes to this device. And so as I've shown the schematic here, I've got 1, 2, 3, 4, 5, 6, 7. That doesn't show the decimal point. I'd have to actually add another one there to affect the decimal point. So I'll do that here, DP. All right. So it's got 7 LEDs built into the package. And they all share a common anode. You can think about that as a common ground or a common negative terminal. And so you remember from last time, we talked about how the anodes are positive and the cathode is negative when you polarize this, and current flows from the anode through the device, and it causes the device to glow, to give out photons at a frequency that depends on the particular semiconductors used to make the LED. The ones that you actually have in your kit are white, so they'll actually glow in a white color. So that's all the colors really of the visible color spectrum in them. And so just don't be confused when we say it's a 7-segment LED, but you actually need 8 pins to program it. It's because it has this decimal point in there. Okay. If you're ever working with these, some of these are common anode and some are common cathode. The ones we have are common cathode. So you don't want to mistakenly use one and wire it up, you know, as another. Okay. This fairly complicated slide here is from the data sheet for the device. You can go look at the bottom of this slide, and I've got the URL for the product. For this product from SparkFun, the vendor that provided it. And it makes sense to go there. I mean, when you're dealing with a device like this, you only have one in your kit. You know, in your kit, you have some things that are kind of throw away. It's okay if you break them. We have plenty of others. You know, we've got thousands of red and green LEDs. You know, these, we kind of have one for each kit. We do have some spares, but we don't have lots of them. So these are a more of a device you have to be more careful with, and it makes good sense that you go and check out for a device like this the product page from the vendor, and then from there you can go and pull up the data sheet, which will tell you, it tells you really more information than you need to know, but it tells you sort of essential information like how to hook it up, maximum voltage and current, and things like that. So go check out that data sheet for that. And let me just tell you, so what you'll find on it and some of the key things, okay? So this device has on it 12 pins. And you have to stare at the data sheet for a while to sort of figure it out. Okay, so you look at this drawing here, and it shows you where pin 1 is. Okay, so that is if you're sort of looking down on it from the top. So you'll notice that there are, back over to the actual photograph of the thing, there's a row of 6 pins. You'll have pin 1 there, and then working up, you'll get to pin 6. And then around back on the other side, you'll have pin 7 over to pin 12. So that's how you, that's where the actual pins are. You can connect this thing into a breadboard. It takes up quite a bit of space. It doesn't leave a whole lot of rooms on the bread. It doesn't leave a whole lot of extra space on the breadboard. You'll actually get, once you plug it into your breadboard, on one side you'll only have 1 row, then on the other side you'll have 2 rows for putting in wires. So you can fit everything in there, but it's a pretty tight fit. I'll be showing you some pictures of it. Okay, so now notice the way on the data sheet things are labeled. So they call the rightmost digit, that's the least significant digit when we program this with numbers, as DP4, right? Down here it's called DIG4. So they're, you know, and here, oh, wait a minute, I take that back. That's decimal point 4. It's called DIG4 here, right? And that corresponds to DIG4 on the schematic, DIG3, DIG2, and DIG1. So digits 1 through 4, 1 being the leftmost or most significant digit, the thousands place, if you were, you know, running it as a 4-digit ring counter, say, DIG4 being the ones place. Okay, now let's take a look at the diagram of this. So look at the leftmost part of this. And what you can see are segments A through G in the decimal point, and you see the corresponding pin designations, right? And this is all for digit 1. So it's actually telling you, you know, the wiring configuration for A, B, C, D, E, F, G in the decimal point. Now it's standard that you would have A is this top horizontal, B, C, this is a standard configuration, D, E, F, and G, and that corresponds to all of these digits. So if you look at the way these are wired, internally, all the anodes for all of them are connected in parallel. So all the A's, all the B's, all the C's, all the, you know, G's and so forth, and all the decimal points are all connected in parallel, and you access those with these pins here, right? Number 3, 5, 10, 1, 2, 4, 7, and 8. So if you put 5 volts on any of those pins and you ground the corresponding common pin, then that segment of one of those LEDs will glow. The key is that if you, so for example, let's suppose you put 5 volts on all of these, right? Then you would expect the number 8 to glow. Well, what you then have to do is ground this common pin. That's the common cathode corresponding to each digit. So all the way over on the right, if you took this one and grounded it, if you put 5 volts on all of those other pins and you grounded this one, this digit would glow. Those other digits wouldn't glow unless their common is grounded. So that's the key to making these things glow, is you've got 8 common anode wires that control the anodes for all of them, but then you have to selectively choose which of the common cathodes you want to ground, and that's going to cause them to glow. Okay, so hopefully that makes sense. It is important to sort of keep in mind DIG4 is the rightmost one, DIG3 going left all the way over to DIG1 on the far left, because we're going to be making use of that in the upcoming material. So let's go ahead and you know, wire this up and make it do stuff. Okay, and so suppose that, for example, I just want to get 1 digit to start with. And all I want to do is have it show 0 and then 1, and then 0 with a decimal point, and then 1 with a decimal point, let's say. Okay, so the way we're going to wire it up is shown on the right. And I'm going to start out using port D, and the reason is that port D is the port that you have available to you that has 8 pins. You have port B, you have port C, and you have port D. And port D is the only one that gives you 8 pins all in one port. So we're going to start out with this because it's just a little simpler. It's going to turn out, we're going to find as we get into it that when we're using port D to control this thing, we end up with a contention or a conflict with the UART, because the UART uses some of the pins of port D. We'll get to that. So, but we'll just starting out for simplicity, we're going to connect some resistors to these port pins, and then we're going to take the common pin of one of the segments and we'll ground it. So that just means if we put a 5-volt on any of those pins, we make them go high, then the corresponding segment is going to glow. Okay, so how do we get a 1? Right? If we want to get a 1, we want B to be high, and we want C to be high, and we want everything else to be low. So what's the bit pattern? Right? Let's come over here and look at it. Here's the bit pattern. Okay, what I'm showing you is all the segments A, B, C, D, E, F, G, and the decimal point. And if I want to glow a 1, that means I want to make B high, and I want to make C high, and I want to make everything else low. In other words, I want to send out to port D the binary word 00000110. Okay, that's what I have here. And it's kind of cumbersome to do that in binary. You can quickly convert that to a hexadecimal value. The upper nibble is going to be 0. The lower nibble, these have weights 8, 4, 2, 1. 4 and 2 is 6. So that just corresponds to a hex value 0x06. So if you write 0x06 to port D and you have it wired up as shown on the right, you'll glow a 1. Okay. All right. How do we glow maybe instead of a 1? Suppose we want to do this, a 1 with the decimal point. Well, that's just going to be down here, the 1 with the decimal point. It's the same bit pattern from A through G, but we'll also turn on the decimal point. So that means we have this bit pattern 10000110, and that corresponds to the hex number 0x86. So those are the ones. If we wanted to glow zeros, we're just going to correspondingly turn on A, B, C, D, E, A, B, C, D, E, and F. And those correspond to, what I'm showing here. Okay. So this is the idea. This is how you sort of figure out how to program one of these things. We're turning these individual segments on or off using bits associated with a port, a GPIO port, and then we're going to be sending a. You can choose to send a binary word to the port. I find it more convenient to do it in hex. Let me show you the code that we're going to use to run this. This is a simple code. All we're going to do is we're going to glow 0, 1, 0 decimal point, and then 1 decimal point. So 0, 1, 0 with a decimal, and then 1 with a decimal. First, I'll just run the little video. Come on. All right, you see, and what it's going to do is it's going to do 0, 1, 0, 1, and then it'll pause, and it'll do it again. 0, 1, 0, 1. Okay, I'm going to run it one more time here. Figure out how. Okay. 0, 1, 0, 1 with the decimal point. Okay, just one thing to note. You'll notice that one of the segments, for some reason, it looks like it's glowing much brighter than the others. And when I went in and looked at that in detail, what I found out is I had used 1 kilo ohm resistors for all of them, except I had drawn a 100 ohm resistor for one of them. So it's because one of those resistors is only 100 ohms. The others are all kilo ohms. That's why that particular segment B is glowing bright. Okay, now let's just take a look at the code. So what does this code do? This code displays the digits 0, 1, and then 0 decimal point and 1 decimal point in sequence on dig 4 of the 4-digit 7-segment LED display. And remember, dig 4 was the rightmost digit. So how are we doing it? Well, I'm setting all the pins of port D to output. This line here is not important, so please ignore that where it says set all pins low. That's for later. Then I just get into a while loop, and I'm writing out the corresponding hex value here that would program a 0. It was 0x3f. We saw that on the previous slide. And then I have a little delay, and I've chosen a delay of 500 milliseconds. And then I write out the hex pattern for a 1, and then a hex pattern for a 0 with a decimal point, and so forth. And then I have a little bit of a longer delay here. So it's pretty simple. I'm just assigning to the port, which means all the pins in the port, this hexadecimal value. So the port pins are going to be high and low, corresponding to the 1s and 0s in that hex digit. Okay, and then I can change the rate at which it's flashing by this delay that I have here. Any questions or anything on this before we get much deeper into this? Now, have any of you seen this before?
We've got one in the front row.
Okay, okay. So let's move on. So what you need to do actually is, for all the digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you can build up a table like this. And I've populated it with most of the digits, but not all of them, because I want you to go through the exercise of figuring out how to do this, yourself. It's simple. I've shown you the pattern, right? You take a digit, you just figure out whether you want A, B, C, D, E, F, G in the decimal point high or low. You sort of write it there. You figure out what your corresponding binary pattern is, the corresponding hex, and then you just write that, right? So you fill out that table. The next version of this, what I want to do is I just wanted to have a loop that just counts from 0 to 9 and back to 0 again. Okay, so now to count 0 to 9 and back to 0, what I could do is I could write this first value, 0x3f. I could have a delay. I could write this value and then have a delay, this value, have a delay, this value, and have a delay, and so forth. In other words, I'd be doing it by brute force. But I'm going to do it a little more efficiently here by using an array. Okay, so here's the code I want to show you. Well, why don't I first show you what it does, and then we'll take a look at the code. It's just counting. And it'll just keep going. It's just counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, and so forth. Okay. So how did we do that? The different thing that we did this time is we created an array. I called it LED digits, and it has 10 elements. This is the hex pattern for 0, the hex pattern for 1, for 2, for 3, and so forth. Okay. Why did I use unsigned char? As I mentioned last time, anytime I'm dealing with something that's only positive, I'm going to make it an unsigned, right? Char, C-H-A-R, is the data type that occupies just 1 byte, so it's an efficient use of memory. Okay, let's look at the while loop here. What I'm doing is I have a variable I. I'm just incrementing it, all right? I plus plus, and if it's greater than 9, I set it back to 0. So this is just the way I've decided to do a counter. It'll count. It starts out, I initialize I with 0, gets into the loop, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back to 0. And then this is the key part. What I'm doing here is I'm writing out to port D. Instead of the actual value I, I'm using I as the index to that array. So that goes up to that array, and it will pull down the ith item in the array. So if I is 0, it'll pull down the 0x3f. If I is 1, it'll pull down the 0x06, and so forth. And then this delay just controls how fast this thing will update. Now, on the code, I'm showing a delay of 10 milliseconds, but for this particular movie that I just showed you, I had a delay of 1,000 milliseconds or 1 second, so it was happening slowly. And what you're going to see as we get into this is the value of that delay is important in a number of ways. Okay, so what I'm going to do now is I'm just going to keep building more and more and more, and we're going to get to the point where we figure out how to put sort of any pattern that we want on here, or any numeric pattern at this point. Okay, I'm going to use the same code as I just had, exactly the same code, except that what I'm doing is I'm taking all of the digits and I'm taking the common cathode for every single digit and I'm grounding that. Okay, so you'll notice here I've got a ground pin, and you can see all of those common cathodes are grounded. So what that means is, in the previous case, I had just grounded the common cathode for dig 4. They're all grounded now. So when we write a value out to port 4, right, and of course you have to have those resistors. We talked about that last time. It's engineering malpractice if you don't have them. But what they will do is they will simultaneously hit the anodes in common for all of them. And then because we're grounding all of the common cathodes, then all of the digits are going to light up. Okay, same code. So let me show you the movie. There it is. All 1s, 2s, 3s. Okay. Now this is with 1K resistors, and this is plenty bright. If I used 100 ohm resistors, it would still work. It wouldn't burn out. We'd be at the upper limit, the upper current limit of these things. My camera view would start to get fuzzy, actually, if I make it brighter, because that just has to do with the way the camera saturates when it's making a movie. Okay, let me just show you 2 more versions of this. And all I'm doing here, I'm going to back up. Let me back up. I'm just going to play around with this delay. Okay, so I just showed you a 1 second delay. Let me show you another one here, okay, where it's faster, all right? So, I'm making the delay sort of a tenth of a second or something like that. Same code, same wiring, all I do is change the delay. Now on this one, what I'm going to do is I'm going to make the delay really small. It's just a few milliseconds. So before I show the movie, think about what's going to happen. I've got all those digits there, and I'm going to be updating them really fast, right? Like 5 milliseconds. What do you think you're going to see when we do this? Well, let's see it. There it is. It looks like all 8s. It looks like all of the digits are illuminated. It's because what I'm doing is I'm running this so fast that your eye actually can't keep up with it. And there's a phenomenon called retinal persistence. And what happens with your eye is it actually retains an image for about 1/30th of a second. This is why movies work. Movies work with a certain frame rate. And when you look at a movie, you see continuous motion. You don't see people starting and stopping and starting and stopping, right? You're sort of being faked out by the fact that you have this sense of persistence here. So when that goes from 0 to 1, there's a different illumination pattern between 0 and 1. But your eye, after the 0 and it goes to 1, your eye still has the imprint of that 0. It's still in your mind. And then the 1, and then the 2, and then the 3, the net effect of all of that is that you just see 8s. I mean, it looked like it was still flickering a little. Let me back it up and see if I can show them again. Okay, after this one, there it is. So the flickering that you do see there is a combination of the frame rate of my camera and some residual flickering in the sense that we're not able to completely fool your eye brain. But the important point that I want to convey to you here is that there is this phenomenon of retinal persistence where your brain will retain an image of something for about a 1/30th of a second. This is why, if you ever take like a sparkler, on 4th of July, and you have a sparkler going and you wave it around in a circle, you'll see the tip of that sparkler making a continuous circle, right? You'll see the long trail of that. Now, obviously, the sparkler at any instant in time is only at one point in that, in that circle, but your eye will perceive that full circle. It'll happen with all kinds of things that are, that are light, and you're fooling your brain because of this retinal persistence. This is the basis behind these displays, because think about what's going on with this display. We've got a 4-digit display, but we've tied all the anodes together, right? For all the A's, all the B's, all the C's, and all the D's are together. How do we use this thing to put different patterns on all 4 digits? Well, what we do is we just do it really fast. we'll throw out a pattern on one digit, we'll throw out a pattern on the next one, the next one, and the next one, and we do that by changing the enable pins. Then we return to the first one, and we do it so fast that your eye is still remembering the previous value due to this retinal persistence. And that's the basis behind these things. So let's go ahead and get further into this. Okay, so on this one, what I'm going to do is instead of taking all the commons and grounding them, I'm connecting all the commons to four different pins. Now, I don't have the code here to show you, but it's simple. All I'm going to do is I have a counter, this ring counter, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to be showing that, but I'm going to also be rapidly sequencing through the different digits. So I'm going to enable PB0, then I'll enable PB1, then I'll enable PB2, and then PB3 in sequence. It'll be obvious when I show you the movie. Okay. See, so I'm writing a 1, but I'm enabling those digits in sequence, and then a 2, and then a 3, and then a 4. Okay, so it's the same kind of code we had, but I'm just changing the value of those enable pins. Okay, now let's sort of put it all together, and what we want to do is implement our 4-digit ring counter, and I want to see all zeros counting all the way up to 9999 on there. Okay, so we want to make use of this persistence effect. Okay, so here's the idea, where we're going to repeatedly illuminate the digits with an update faster than 1/30th of a second, because our eyes and our brain can't discern the difference if we do it faster than 1/30th of a second. In other words, I'm going to write a value to one of the digits, then I'm going to go off and deal with the other digits. I have to return back to that first digit within 33 milliseconds. And if I do that, your brain will see a continuous display, even though I'm going to be writing to one digit, right? I'm going to write something to it, and then I'm going to shut it off. I'm going to darken it, and I'm going to go to the next digit. Then I'll darken that and go to the next digit. I'll write something, darken that, and go to the next one. And darken that, come back to the first one, and I'm doing all of that within 33 milliseconds, and I will have fooled all of our brains because our eyes are hanging on to those pictures for 1/30th of a second. Okay, so let's look at the pseudocode here. All right, we'll turn this into code on the next slide. But I'm going to have a counter that's incrementing between 0 and 9999. I'll illuminate the ones digit. That's the least significant digit. And I'm going to illuminate it for 5 milliseconds, just 5 thousandths of a second. Then I'm going to shut it off. And I'll illuminate the next digit for 5 thousandths of a second. Shut it off, illuminate the hundreds, shut it off, illuminate the thousands, and then I'll repeat the whole thing. So I'm going through this whole loop here every 20 milliseconds. Okay, so the least significant, they're each going to be only illuminated, strobed for 5 milliseconds, but they're revisited within 20 milliseconds. And take a look at what you see. So if you look on, on the left, that 3, that 4, that 5, they look continuous to you. You can't see when these things are shutting off. They're only on, each one is only on a quarter of the time. They're only on for 5 milliseconds out of 20. But because of this retinal persistence effect, it seems like it's on all the time. Now, what happened here? Why is it when it's done, we had that black spot there? Well, that's my camera. My camera took a picture of it, and actually it's able to grab individual frames. So it just happened that the very last frame that my camera grabbed when making a movie, it happened to catch one of these being dark. Okay, so this is the code that we just used for that. Okay, and now so the code itself, it's not that complicated, but it's technical in the sense that there's a technique here, and there's a lot of specifics we have to know in order to make this right. And that's kind of the nature of this embedded programming. There's a lot of sort of, specific things you have to know how to do it. You need to know the technique and the pins and all that for it to work. But the code itself is quite simple. Okay, so let's just read what is this code doing. Okay, this code demonstrates the use of a 4-digit 7-segment LED. This version counts 0 to 1,000 repeatedly and uses retinal persistence to create an always-on effect in the digits. So it's the same code we looked at previously, except that, what I'm doing here, well, let's go and look at it, sort of piece by piece. We have that array that defines the hex bit patterns. Okay, unsigned int I equals 0, that's just my counter. This is my ring counter. And, I plus plus, I'm incrementing I. If I is greater than 9,999, set it back to 0. So that's straightforward. Okay, I'm using port D as my 7-segment pins. So I'm making those output pins. I'm using port B as my enable pins, right? Those pins, when I set one of those pins low, it's going to enable a particular digit. So that's what that's about. And in this line here, port D is equal to 0xFF. I'm just setting all the bits of port B high. That will disable all the digits. So initially, everything is off. Okay, we get into the loop. We've got our counter. All right, first thing I do is dig 4. That was the ones digit. I just compute what that number is. And then I program the port. And then I enable that digit. And what I'm doing is I'm setting pin 1 low. I'm setting the enable pin, that is that common cathode, corresponding to dig 4. I'm setting that low, but all the other ones are high. And I wait a little bit, and then I do the next digit, and the next digit, and the next digit. Okay? So that's how it's done. Now, I'm just going to show you sort of another version of that. This code runs fast, right? That was the thing about it. If I go back, if we run this, let's see, you can see it runs, pretty darn fast. How do we slow it down? All right, how do we make this thing, instead of counting, it's going through this whole loop, and the loop is updating at 20 milliseconds. But suppose I want a slow counter, right? I want to slow the whole thing down. Well, what I have to do is have sort of a loop inside a loop, because this action here has to be tight. All of this, to fool the eye brain, this has to repeat at 20 milliseconds. So what I have to do, if I want to slow this whole thing down, is do this whole thing many times as an inner loop controlled by an outer loop. And that's what we're going to look at here. So let me just show you the examples. Okay, here's one where it's counting pretty slow. That's 9. This is an overall delay of 1,000. And obviously it would take a long time to count all the way up, to 9999. On the right, this one is just a little faster, right? But I just wanted to show you how you can modify the code so that you can make it count at any rate you want. So what I've got here is sort of an outer loop that's controlling the counting, right? The ring counter. But then inside I have this tight inner loop that's illuminating these digits with a 20 millisecond update cycle. Okay. So, here's the code. I don't think I'll necessarily go into all of it, but I'll just show you that I have this outer while loop here, and then I also have an inner loop. Okay. And the way I do it is I define 2 variables. Count time, that's the total number of milliseconds between counts. So whether I want that to be 1,000 or 200, that's the time, the time base of the whole thing. And then I have my persistence, which I'm keeping at 5 milliseconds. And then when I loop here, I'm just dividing count time divided by persistence, right? And I'm also dividing that by 4 because I'm doing this stuff in sequence. So basically, I've got this inner loop, and I just keep running through that at 20 milliseconds, right? I just keep doing that because I need to do that for this eye-brain thing to work, right? How many times do I do that? Well, that depends on how slow I want the whole thing to be, right? And that depends on the numerator here, count time, okay? So the bigger I make count time, the more times we'll go through this inner loop. Now, there are other ways of doing this. You can use what's called interrupts, and we'll say a little bit about interrupts toward the later part of the course. But this is certainly a valid way of doing this. Now, Right now, all we're doing is we're sending the digits to the 7-segment 4-digit display. Let's see, I got a question here that has come up. Okay, someone said, it doesn't look like I'm switching the lights off. And how am I toggling them on and off? So take a look at this line here. What I'm doing here is I'm programming all the anodes, and then on this line down here, port B is equal to the complement of 1 shift left 2. What that's doing is it's making one of those enable pins low and all the rest high. That's what that pattern would be, right? Because 1 shift left 2 is going to be, a bunch of zeros in a 1 in bit position 2, and then more zeros. Complement that, and you have all 1s with 1 hole in it. And remember, these are common cathode. You have to ground that cathode. So what this line will do is it'll ground 1 in only one of the cathodes. So the concept here is I'll do this first one, and I will ground the cathode corresponding to, it's dig 4, right? And then I'll ground the cathode for dig 3 and dig 2 and dig 1, right? So I had this question that came up in the chat. How are we toggling these on and off? That's how I'm doing it, right? I'm enabling and then effectively disabling them as we go from one to the next. Okay. Now let's take that same code and stick into this the code that will allow me to also write out to my serial monitor. So I have that. This is important because you're building one of these things. There's a lot of wiring going on in this. And, the first time you try to make it, the LEDs aren't looking right. So by also writing the information out to the serial monitor, you can see what's showing up on the screen. You don't have complicated hardware there. And so the only difference here is I pulled in my UART codes. These are the UART functions that we're always talking about, okay? And I'm just, chucking in here a UART send line, right? I have my digit, and we looked at how to do this at the beginning of class last time. But what this will do is it'll take that digit, convert it to a corresponding ASCII value, and then transmit that out via UART. So that's, so I'm doing the thousands digit, and then I'm doing the hundreds digit, the tens digit, and the ones digit. So here I'm doing both. I'm sort of, I'm sequencing through this fast, and I'm illuminating the LED. I'm pushing the digit out via the UART. When I get down here, I have those carriage return and new line or line feed. What that will do for the UART is it'll move the cursor over to the beginning of the line, rather than just have all those digits sort of show up one after the other. It's just putting it's like hitting an enter key after each one. So now let me show you the code here. And so what you're going to be seeing is the display from the UART on the left. Okay, that's all this. You'll see that scrolling, and then you'll see the the LEDs, which are obvious. But I want you to pay attention to segment B, because there is a problem here. So pay attention to segment B. That's going to be this one here. And so I may have to run this twice for you to see the problem. Once we get this going, okay, you see your count here, zeros and ones and twos, 3, 4, 5, 8, 9, 10, 11, 12, 13, 14, 15. Did you see what happened when it hit 15? Segment B stayed on, right? And so I'll run this again, and I want you to just keep an eye on that segment. I'm sort of jostling the camera, but this circle will settle over to that pin. Take a look, 4, 5, pin segment B is coming on when it shouldn't be coming on. And so there's sort of an important gotcha here. You can see this display makes sense, right? It's showing us, 19, 19, 19, 19. It's going through 20, 20, 20, 20. That all is working, right? But we have this problem here. Okay, what's going on? Well, the reality here is that we have a contention here over pin PD1. And here's the issue. Recall from when we talked about the UART that the UART uses PD1 and PD0 for receive and transmit. We're only transmitting. And so since we're transmitting via the UART, we're making use of pin PD1. Okay, so let's just pause for a minute and take a look at this pin diagram. You'll notice that each of these pins has multiple things that it does. So taking, for example, this pin here, it can serve as GPIO pin C5. That's port C, pin 5. It also functions as ADC 5. That's analog to digital converter 5. It can take an analog signal in. It's also the serial clock line for something called the I2C interface, right? And it also serves as interrupt 13 for port C. So each of these pins is capable of doing many things. And you may recall when the first thing we do when we want to use the UART is initialize the UART. And the first thing we do there is we enable it, we turn it on. Well, when we do that, what that means is we're allowing this pin to transmit our serial transmit data via the UART. And so the problem that we've got here is, you only have a certain number of pins in this chip. And so we knew that we needed 8 segments to control this 7-segment display plus, decimal point. So my suggestion was, well, let's use port D, because port D has pins 0 through 7. It has a full byte there. And so if they're shown in the red box, we've got, 0, 1, 2, 3, 4, 5, 6, and 7. I mean, that's convenient. We have that whole port. But the problem that we had is that since this pin is doing double duty, it's actually being impacted both by our programming the LED and by what the UART's doing. And so that's why we were finding that segment B, because this is, not this one, it's this one, it's PD1. PD1 was the one that went to segment B. So that's why we were having that contention issue. How do we solve that? Well, we have to avoid using those pins. Certainly the transmit pin if we're just transmitting via UART, or if we wanted to actually take in input from the keyboard, we haven't done that yet, but if we were using our serial monitor both two-way, someone working on the keyboard and we wanted to receive information from the keyboard, that would be using another of these pins. Okay, so the solution is to avoid PD0. Just don't, if you're going to be using the UART, don't use PD0 for GPIO. So there are, many ways that you can do that. It does require that you get into some bit twiddling here to sort of, because what you want to do is write to port D with a full byte. And here we're going to have to take away one of the bits of that. And so I find it convenient when you can, if you can't work with a whole byte, work with 2 nibbles, right? 2 4-bit chunks, because each one conveniently corresponds to 1 hex digit. So what I'm going to do here is I'll go back to the previous slide, and we were using all of port D to control the segments of the LED, and we were using port B here, for the enable pins for those common cathodes. Well, what I'm going to do instead here is just use the upper nibble of port D. Okay, so that's pins 4, 5, 6, and 7. And then for the lower nibble of that byte, I'm just going to grab these from port C. So I need the 8 bits to program all those anodes. I'm going to grab, I'm going to get I need a byte's worth. So I'm going to use the upper 4 bits of port D and the lower 4 bits of port C. Okay. And here's the code to do that. This isn't necessarily the cleanest way to do it, but it works just fine. What I'm doing is I'm writing to port C, and then I'm also writing to port D. And I'm only pulling wires off of the upper 4 bits of one and the lower 4 bits of the other. And when I go ahead and do that, let me just show you 2 versions of the code. Okay, it starts running. Look for the 5. See, there's the 5, and we don't have that contention problem. Okay, and I'll show you the other one. It's going faster. Oh, here it goes again, right? But it solves that problem. Okay, so this gets you to the point where you can program one of these things. You take advantage of the retinal persistence. You can figure out how fast you want to do it. You can also send the data to the monitor via the UART. Okay, so there's quite a bit here, but as I've emphasized several times, the code in itself is not all that complicated compared to coding from data structures or even for some of the other things that you did in your first programming class. We're just working with a while loop, but the key is you have to know how to twiddle all those bits. Okay, all right. That's all I wanted to say about that. And the next thing that we need to get you up to speed on is how to use this analog to digital converter. And so what I wanted to show you on this chart here, first of all, is I wanted to sort of review a bit, right? The very first thing when we introduced this, this big block diagram, that is an architectural diagram of our chip, our microcontroller chip. So the very first thing is we said, let's start to work with these ports, GPIO pins, and we can set those high and low. And the code for doing that looks like this up here, right? I mean, you do data direction registers, port registers. Then in your while loop, you're checking to see if pins are high and low. That's kind of how that's done. So we covered that, and we've been doing that for a while. Then we introduced the UART. Okay, the data sheet calls it a USART because it also has a synchronous mode that we don't use. It calls it USART 0 because some chips actually have several USARTs or UARTs on them. But don't look at the details, but see if you can sort of look at the general structure of the way we did the USART code. Starts out, you've got some stuff to initialize it, and then you've got a while loop, and you're checking some bits in there. And notice the similarity between the way we did this one here and the way we did this. Not in the specifics, but in the general notion. The first thing you do after int main void is you're initializing. You're setting things up the way you want. How fast you want it to be, whether it's input or output, you're doing your initialization. Then you get into a while loop, and in that while loop, that's where sort of the action is taking place. Is this switch pressed or not? And if it is, turn on this LED. And in this one, it's is the UART buffer busy? And if it's not busy, let's send out a character. Right? And I just wanted to show you these because the look and feel of all of this peripheral programming is kind of similar. There's some initialization commands, and then there's the stuff that you do repeatedly. So what I'm going to show you on Monday is how to do the analog to digital converter, right? And it's similar, right? I mean, the specifics and the registers are different, but we're going to introduce this block up here. And we'll start out, by initializing some stuff. All right, how many bits? How fast should it convert? Which pin should it be looking at? All that kind of stuff. And then we'll, get in here and we'll start to figure out how to actually sample with the analog to digital converter. So you'll see that the coding pattern here is sort of similar to these other things. Okay, so that's on Monday, and now you'll have all the pieces to do Lab 3. On Wednesday, as I said before, that's just Q&A. I'll come into the class with no agenda. I'm just there to take any questions that you have. So I'm done with you now, letting you go, giving you 30 minutes of your day back. I do need you to go into the lab, pick up that bag of parts and those clip leads. And I encourage you to start working on this sooner rather than later, because as you can tell, there's kind of a lot to it, right? Between the LEDs and the persistence and all the wiring and the resistors and the getting the timing right, sending the data to the UART, dealing with that contention, quite a few wires there. And then once we add the analog to digital converter, it's another piece. So it's a fair bit of complexity in this. So do start it early so that you can come in next week, a week from today, and ask me any questions you have. Okay. So with that, I'm done here unless you have any questions or comments.